Email yesterday afternoon asking you to take a very short survey. It's 15 seconds. All it asks you to do is to go in there and indicate what science class, if any, you signed up for next year. I assume you did, because
And I also send you an email with the link, or the link to the notes if you'd like to pre-made notes. Yes.
if you didn't download the note sheet for Notability, it's not a big deal. We're going to go through a number of things, but for the most part, anything that I'm going through, you can just write down the definition of the word or the equation as we go along, so you don't have to have that note sheet, but certainly it would be nice to have it to refer to. You should have 3 handouts from when you walked in. Equations 3, equations 4, and the chemical reaction survival guide. Okay, let's get started then. Last week, Mr. Gussie did the presentation on chemical reactions just overall. Talked about signs of a chemical reaction. We'll review those. Talked about the Flintstones and a number of other things. Today we're going to focus specifically on our replacement reactions, single replacement and double replacement reactions. Before we do that, quickly remind you of what we're looking for when a reaction takes place. How do we know if a reaction takes place? There's 4 general signs. The first is a color change. These are not worms. Those are, on the left-hand side, a chain that is still in its original metal form, kind of a silvery white metal, and then on the right hand side it's rusted, which is an oxidation reaction. It's a reaction with the metal and oxygen from our atmosphere. When things oxidize, they rust, or when they rust, they oxidize. And that results in a color change. Second one, we've got bubbles produced, which indicates that there's a gas produced. That's why we do the splint test, which is one of the things that you responded to in your post-lab question from our chemical reactions lab from last Friday when you did the quiz and the post-lab conclusion on Monday. So if we form hydrogen gas, whoop, and if we form carbon dioxide gas, the flame goes out, and if we got oxygen gas, it just continues to glow because things burn in the presence of oxygen. Oh, I can remember at least one of you in particular that when we did the magnesium strip and the hydrochloric acid reaction on Friday, some of you were holding that test tube in your hand, and some of you got tired of holding it very fast because it got very hot, and you did a lot of this. Somebody get me a test tube clamp. This is hot. That is one of our chemical reaction signs. That guy generated a lot of heat. And then finally, if we form a precipitate when we mix 2 solutions, that's going to be the sign of a reaction in our double replacement reactions, which is going to be the second of the 2 types of reactions that we discussed today. All right, here's just a couple of slides that show you some chemical reactions taking place. That is obviously time-lapse photography. That's formation of a metal similar to what we did in our either-or lab. This is an explosive reaction. Mr. Gussie talked last week about the AP chemistry students having the touch-sensitive chemical reaction. that explodes. This is the reaction we did last week with the ammonium dichromate. And then finally, here's two solutions being mixed and forming a precipitate. Ooh. Pretty neat. Okay. So, how do we know if we have a chemical reaction, or if we're mixing a couple of chemicals, if a reaction is going to take place? Because just because we put two things together doesn't mean that they're going to connect, that they're going to interact and form some chemical bond. So we've got the activity series that's listed to the right of your chemical reaction survival guide. It's also listed to the right on both sides of equations 3, which we'll refer to in just a few minutes. It's really a measure of how reactive or how active each of these elements are. The higher they are on the list, the more active or reactive they are. In terms of the Wilma and Betty and Barney and Fred scenario, the higher on the list, the more of a bully they are, the more likely they are to kick somebody else out. So we're going to focus on our loners. In each of these equations, we've got one loner. Iron is our loner, nickel is our loner, lithium is our loner, aluminum is our loner. We want to find out if our loner is a bigger bully than a guy that's already matched up with somebody. So is iron more active, more reactive, or more of a bully than copper? If he is, he's going to kick copper out of that compound and replace him. He's going to go out of the dance floor and say, copper, you're out, I'm in, now she's my girl. So when we look up here, we see iron is above copper. So iron is more active, more of a bully. It is going to replace copper in that compound. When we write our chemical formulas or our chemical equations, a metal is always just written as elemental. Metals are not going to be diatomic. Our diatomics are the hecnohalogens, and there's some other mnemonic devices for remembering that. But metals are not going to be diatomic, so when we write them in the equations, it's just the element symbol. And when they're replaced, if they end up being just a single metal, they go back to just being one of them. Okay, so here we've got copper 2. We know that because sulfate, SO4, is a 2- charge. There's one of each. And so that would be copper 2 sulfate. Over here, we've got iron 3 sulfate. And again, we can recognize that by looking at our formula. SO4 3, that's going to give us a total of a -6 charge from our sulfate. So we've got to have a +6 from our iron. So we're going to have 2 of them at +3 each. Nickel and sodium. Nickel's down here, sodium's up there. Sodium's having no part of this. Sodium's staying where he's at for that. Those are easy. You just write no reaction. Lithium and zinc. Lithium's way up here at the top of the pecking order. Everybody wants to dance with lithium. Zinc, way down here. So lithium is going to replace the zinc. Lithium is a +1 charge. Carbonate is a -2 charge. So we're going to need 2 lithiums to combine with 1 carbonate. And zinc is sitting by himself. And then finally, aluminum and copper. Copper is way down here. There's not too many things that are less active than copper. So copper is very commonly replaced. In this case, aluminum is going to replace your copper, and we're going to end up with aluminum chloride. Aluminum has a +3 charge, so we're going to need 3 chlorines instead of just 2. Now these are not balanced. We'll worry about balancing in the later examples, but the products are written out using our crisscross or reverse crisscross so that we know that they are all neutrally charged products. Any questions so far? Okay, let's look at the bottom of your activity series. In addition to all these metals, you've got halogens, fluorine, chlorine, bromine, and iodine. Same process. We don't always have to have metals replacing metals. It can be non-metals replacing non-metals. So in our first one, we've got chlorine and bromine as our non-metals. Sodium is the only metal. So we're going to have a positive ion of sodium with one of these negative ion halogens. Chlorine is above bromine, so it's going to replace it. More active, more aggressive. Get out of my way. Here you'll see that chlorine is written as Cl2 because it is a diatomic. That's our hecnohalogen. So when we write our products and know that bromine got replaced, it's now going to be elemental bromine, so it's going to be a diatomic. There's always two bromines bonded together, and our two chlorines become just one. If we were going to balance that, of course, we'd have to put a 2 in front of there. So we'd have 2 on both sides and put a 2 in front of there. Iodine and chlorine. Iodine's way down here, chlorine is up there. So iodine doesn't have what it takes to replace the chlorine. No reaction. Right, these things practically do themselves. And back to metals, magnesium and nickel. We're over here, magnesium, nickel. Magnesium's got a little more something than nickel, so it's going to be a little more aggressive, a little more active. It replaces the nickel, and our new compound is magnesium fluoride with just nickel. So far, so good. Any questions? Too fast? Hearing nothing, we're moving on. Okay, let's look at equations 3. I'll do a couple for you or with you. All right, this is going to be like equations 2, where you were given the worded equation and you have to write out the formulas and determine what and if the products are. On equations 2, we told you that this reacts with that and produces this and that, so all you really had to do was replace the names with the formulas. Now we've got to figure out if a reaction is going to take place, and if so, write out the products. So we got copper and iron 2 nitrate. Copper is just by itself. Copper is just by itself. And we've got iron 2 nitrate. Iron 2 tells us that the iron is going to have a +2 charge. We don't really have to write that up there, but we can. And nitrate. NO3, that has a minus charge. So a little crisscross tells us that we're going to need 2 of those for 1 iron. What are we going to get for products? Does a chemical reaction take place? We look over here at iron and copper. Really want to focus on our first one, our solo copper. Where is that relative to the guy that it's trying to replace? The other positive ion would be iron. It's below, so it's less active. As a result, nothing. I'm only writing these above so that when you get to number 7, I'll be writing there rather than down here again. Sodium and dihydrogen monoxide. Sodium is Na. What is dihydrogen monoxide? H2O. That is just a fancy, super impressive way to say water. But we're going to write it not as H2O. We're going to write it as HOH. And that's just to help you out in a couple of different ways. One, it'll be easier to see what's happening when you're determining your products, and it'll be easier to balance. And really, when chemical reactions take place with water, they're breaking water down into 2 ions. The OH is our hydroxide negative ion. That makes things basic. The H plus is the hydronium ion. That's the ion that's present in acids. So more hydronium ions, lower pH, more hydroxide ions, higher pH. You may not know anything about that yet, but you will soon. Okay, what's going to happen? Our 2 positive ions are sodium and hydronium. So we're looking at sodium and hydrogen. If the sodium kicks out the hydrogen, what's it going to form? H2. If hydrogen was the solo guy by itself, it would be H2. So don't let the fact that it's written as H2 over there in the activity series get in the way or confuse you at all. So we're just comparing hydrogen and sodium. Sodium's way up here, hydrogen's way down there. So the sodium is going to replace the hydrogen. You're going to end up with NaOH plus H2. So in this one, a reaction does take place. We would then want to balance this guy. We've got 3 hydrogens on the right, 2 hydrogens on the left. If we put a 2 here, we'll have 4 hydrogens. And then we can put a 2 there to give us 2 and 2 more for 4. That also gives us 2 sodiums, so we need a 2 over here to balance that equation. I keep trying to get out of the way, and I don't have to. Nice. Questions on that one? Zinc, sulfuric acid. Zinc is just a metal, so we write that just as its element symbol. Sulfuric acid. Those darn acids, what the heck was the formula for sulfuric acid? I know it's an acid, so it's got to have an H. And I know it's sulfuric, so ic means 8, which means it's sulfate ion, so it has to be SO4, which has a 2- charge. So I'm going to need 2 hydrogens. Question, Carly?
Oh, wrong.
You had a question, I heard you.
I just asked if we need parentheses.
You don't need parentheses. The only time you need a parentheses for these polyatomic ions is if there's more than one of them. I don't think that it's wrong to write it as H2SO4, but the only time you would need to write it is if you got 2 or 3 of them outside of it. Okay? So we got zinc and hydrogen again. Zinc, ooh, there he is. There's the guy. Hydrogen's down there. Zinc's the bigger bully. Zinc is kicking out the hydrogen. So we're going to end up with zinc sulfate plus hydrogen gas. 1 sulfate, 2 hydrogen, 2 hydrogen, 1 zinc, 1 zinc. Giddy up. Balanced. Yes, sir.
Does it matter if the hydrogen goes in front or back?
No, when you write the products?
Yeah.
Nope. Makes no difference if you write H2 plus ZnSO4 or flip them around. We got this and we got this. Doesn't matter which one we say first. We kind of Yep. When I did this one, this is right. And I said, again, what the reason I wrote HOH is not because it's different than water, but just because when water takes place in a chemical reaction, it's a little easier to see what's going on, because what really happens with the hydrogen or the water is that it breaks up into H and OH ions. And so if we write it as HOH, it's a little easier to see that we're going to have this hydroxide ion as our negative ion in the replacement reaction. It's not wrong if you write it as H2O, but we just feel like it's easier to see what's happening if you write it as HOH. Is that okay? All right, our last one here is fluorine and sodium chloride. Fluorine plus NaCl. So far, so good? No. Fluorine is diatomic when it's by itself. So we got F2 plus NaCl. We come over here and look at the relative activity of those two. Fluorine is above chlorine, so chlorine's getting the boot. So you're going to have how's that? Is that what you wrote? FNA? If you did, I wish you hadn't. Don't write FNA. Because when we write our chemical formulas, okay, that's working well. We always write our positive ions first. Metals first, then your nonmetals. And again, chlorine is diatomic, so that's going to become Cl2, which means that we need two chlorines over here, which means we need two sodiums over there. Those are single replacement reactions, and that's really all there is to single replacement. Well, I'd say that's all there is, but that's as much as I need to tell you about single replacement reactions. Any questions? Okay, a little less whispering, a little more in terms of questions. If you have something to say, you can just raise your hand. I'd be happy to try and answer it for you.
Keep going outside.
Alrighty, let's take a look at the flip side of your note sheet. If you don't have that note sheet, then you can look at equations 4. It's got the same information. Solubility rules. A lot of stuff here. This is not stuff that needs to be memorized. This is a reference table that you will be able to reference. But it's still in your best interest to become familiar with it so that you don't have to waste a lot of time going back to look at the same dang thing. Shoot. That's So some of these should become second nature. Darn it. In any case, what we want to do is look at our chemical reaction, apply our rules of solubility to determine if a reaction takes place, if it doesn't. First thing we need to recognize in terms of solubility is what the heck does solubility mean? If something is soluble, soluble has the same root as solution, SOL. If something is soluble, it dissolves in solution. I know what you're laughing at. It's precious. So, on your note-taking sheet, what I would encourage you to write next to soluble equals, on your note-taking sheet, if you downloaded it from Notability, if you didn't, you can still write soluble equals, or soluble means dissolves in solution. Soluble means dissolves in solution. If something dissolves in solution, that means it is aqueous. So after you write dissolves in solution, I would encourage you to write AQ in parentheses. If soluble means that it dissolves in solution, not surprisingly, insoluble means does not dissolve. If it doesn't dissolve, that means it's going to remain a solid. So let's have a little look-see at an example. PbNO3 2 plus Ki. What do we have here? What's this guy going to be called? Who can tell me what the name of this is? Lead nitrate? Is that good enough? It's lead 2 nitrate, because our nitrate ion has a -1 charge. There's 2 of them. So this is +2. Our lead has to be, I'm sorry, this is -2. So our lead has to be +2. So it's lead 2 nitrate, which is different than, say, lead 4 nitrate. And then over here we've got potassium iodide. Right here we have potassium iodide. Actually, we don't. Right here we have dihydrogen monoxide. And here we have potassium iodide, which is soluble. So when we put a little bit of that in our water and we give it a little stir, we end up with a clear, colorless solution of potassium nitrate. Not potassium nitrate, potassium iodide. This is lead nitrate, lead 2 nitrate. I got a little bit too much in here, so some of the lead nitrate is settled out to the bottom. So I put just a little bit more than what we can dissolve in that amount of water, which there is always a limit to how much you can dissolve. There's a saturation point. If you dump a can of salt into a glass of water, it's not all going to dissolve. You'll end up with salty water, and then you'll also end up with a bunch of salty sludge at the bottom. So at some point, your solution becomes saturated. In any case, we've got a lead 2 nitrate solution here. and our potassium iodide solution there. If Mr. Gussie is zooming in right now, then we can proceed with the demonstration. Okay. So both of those are dissolved in solution, so they're both going to be aqueous. In a double replacement reaction, our two positives are going to switch places, or our two negatives are going to switch places. But either way, we've got two couples that are switching partners. Positives always go with negatives, so our lead is going to switch over to the iodide, and the potassium is going to switch over to the nitrate. The lead and the potassium will never go together because they're both positively charged. Our nitrate and our iodide will never go together because they're both negatively charged. Now we want to determine if this actually will take place. What's going to happen? Well, how are we going to find out? Well, we're going to refer to our solubility table, or our rules of solubility. Let's start at the top. We've got nitrates. Nitrates is the first rule. That's an easy one. That's one that you shouldn't have to refer to your rules of solubility for after a couple of times because it's always soluble. There are no exceptions to nitrates being soluble. If you've got a nitrate compound, it's soluble. Except when? Except never. It's always soluble. Next, we got alkali metals. Well, do we have any alkali metals? Sure we do. We got potassium right there. When are alkali metals soluble? Well, lithium, sodium, potassium, cesium, rubidium, and ammonium soluble. When? Always. So both of those are soluble. We know then that that is going to be aqueous. The question is, if a reaction takes place, are we going to form a solid? So let's look at our next rule. Next rule deals with our halogens. Iodine is a halogen. Iodine, or the halogens, are soluble. Except, hold your horses, except when we got silver, lead 2+, which is a big deal because we identified it was lead 2 over there, or mercury 2. So that means it's not soluble because it's one of the exceptions for the halogens. If it's not soluble, it's going to form a solid. If a solid forms, that means a reaction has taken place. What will it look like? It's going to look like this. Big old jug of potassium iodide. That's our big beaker, little beaker, lead nitrate. Let's put a little bit in here and see if we can see anything happening. What? Got some stuff there. So it looks kind of like a yellowish smoke, but it's really just a bunch of tiny little particles, like very fine sand that is formed and is settling out to the bottom. A lot of people think that more is better. So what's our yellow stuff? Our yellow stuff is our solid, our lead iodide. It's pretty neat, huh? You're going to do a whole bunch of these reactions in lab. Not macroscopic levels like this where you're mixing 15 liters with 200 liters, but a couple of drops with a couple of drops. Let's look at another one. Sodium sulfate, barium chloride. Both aqueous. We flip our positive ions, do the old double switcheroo. Sodium goes over here with the chlorine, Barium goes with the sulfate. It's balanced. We got two sodiums, one barium, one sulfate, two chlorines, two chlorines. That's all good. So our rules of solubility. Sodium chloride, is that going to be soluble? Well, chlorine is soluble except with silver, lead, or mercury. So that's a yes. We should double check on the sodium. Well, the sodium is actually Rule 2 above Rule 3, and our alkali metals are always soluble, no exceptions. So those are both yeses, which means that's going to be aqueous. Sodium chloride dissolves, and you know that because salt water. Barium sulfate. Sulfates. Sulfates are soluble, except, well, that dirty dog is a barium. Barium's not soluble. So if our barium sulfate is not soluble, that means we're going to have a solid. So we mix those two solutions, you're going to see a cloudy precipitate fall out of solution. One more. This is written backwards on your note sheet. On your note sheet, I think you have NaOH plus MgBr2. Is that correct? Yeah, so those are actually, what you have listed as your reactants are actually your products. Those are both aqueous. The NaOH and the MgBr2 are the products. And going quickly, our sodium, always soluble. Hydroxide, slightly soluble, but still soluble. MgBr2, Br, soluble, except silver, lead, and mercury. Well, that's okay. That means that both of these are aqueous. Watch this, Alec. Watch what happens to the aqueous. They're dancing. Everybody knows what dancing aquei means, right?
Yeah, obviously.
That means that we started out with basically 4 ions dissolved in solution. Magnesium ions, hydroxide ions, all dissolved in solution. Sodium and bromine, all dissolved in solution. When we mix them, they're both aqueous. So we still have 4 ions, all dissolved in solution, which means that really nothing has reconnected and formed a new compound that fell out of the solution. So essentially, nothing happened. No reaction, no reaction. No precipitate, no reaction. If there was some way that we could emphasize that to you, we would. No precipitate means no reaction. That's probably worth writing down. No precipitate means no reaction. How do we know we have no reaction in a double replacement reaction? No precipitate. Okay, let's do a couple. Equations 4. This is your worksheet. What do you do with that guy? Numero uno. Silver nitrate and barium chloride. First thing we do, do our double switcheroo and write our new compounds. So our silver goes to our chlorine, our barium goes to our nitrate. Silver, always +1. That's one of the two metals that we said are kind of exceptions that you need to memorize. Silver is in family 11, last digit 1, always has a +1 charge. Zinc, family 12, last digit 2, always has a +2 charge. So our silver and chlorine are going to go together 1 to 1. Barium has a +2 charge, nitrate has a -1 charge. So we're going to need 2 of them. That's a little crisscross without writing it all out for you. Over here we have 2 nitrates. Over here we have 1. So we put a 2 in front of our silver to get us 2 nitrates, which gives us 2 silvers. So we put a 2 in front of our silver to give us 2 silvers, which gives us 2 chlorines, and that's what we have, and 1 barium and 1 barium, and giddy up. So now we check our rules of solubility. Anything happening here? Let's start with nitrate. Nitrates are soluble. When? Always. We don't have to look any further. Because nitrates are always soluble, we don't have to look for anything that deals with barium. Silver is not an alkali metal, so we can skip that guy. But chlorine is in rule number 3. And that is soluble, except when it contains silver, lead 2, or mercury. Well, that's silver. That dirty dog is going to make that a solid because it is insoluble. And we're done with that one. Sodium phosphate, magnesium hydroxide. Go ahead and switch your ions. Our sodium is going to the hydroxide. Our magnesium is going to the phosphate. How many sodiums do we have for our hydroxides? +1, -1, so that's fine. Magnesium is 2. And phosphate is anybody got a chemical reaction survival guide? -3. So we're going to need 3 magnesiums, 2 phosphates. Well, that's more than 1, so we better put that guy in parentheses. Huh. Yeah. Otherwise, it's going to look like we got 42 oxygens. Okay. That's fine. Sodium hydroxide. Sodium. Soluble. Nice. Just a little double check. Hydroxide. Most hydroxides are slightly soluble. Sodium hydroxide is soluble. We might want to come back and take a look at this slightly guy, but sodium hydroxide is soluble. So that's aqueous. Magnesium phosphate. Where is he?
Sodium what?
Magnesium phosphate, not a nitrate. Magnesium's not an alkali metal. Neither of those are halogens, not sulfates, not hydroxides. Here we go. Rule 6. Sulfites, carbonates, chromates, and phosphates. They are slightly soluble. Slightly loses to soluble. If it's slightly soluble in a mixture with something else that is soluble, it's going to form a precipitate. Bless you. And we got one last one. Potassium nitrate and barium chloride. That's going to give us barium nitrate, which we just determined up here needs 2 nitrates, and potassium chloride. And again, Carson asked earlier, does it matter what order we write these in? It does not. So whether you write barium nitrate plus potassium chloride or potassium chloride plus barium nitrate makes no difference. Nitrates, always soluble. Always soluble. That says aqueous right there. You can't see it, but that's what it says. And potassium chloride. Potassium, always soluble. Chlorine, soluble except silver, lead, mercury. So it is also aqueous. You know what that gives us? That gives us dancing aquei. Which means no reaction, because there is no precipitate. Got 2 more things for you. One is a little bit of good news, and another is a little bit of a video. The little bit of good news is that you're getting a lot of worksheets in the next couple of days. That doesn't sound like good news yet, but because you're getting a lot of worksheets in a couple of days, we are going to ask you to do all of the evens on equations 3 and 4. The odds are optional, certainly encouraged, not required. And since we have 5